Okay, so this is the last review video. It's all about subatomic modern physics. And we talk about matter on a subatomic scale. Energy and matter can be interchangeable, and that matter can become energy and energy can become matter. And that's Einstein's famous equation, E equals mc squared. Okay? This is the mass in kilograms of the matter, and this is the energy in joules. They can be converted into. Okay, and this is speed of light squared. So if you were to graph energy versus mass, every now and then they throw a question on there like this. And it shows this, and it wants to know what the slope of the line represents. And a lot of times it confuses people because they're not sure, if they're talking about energy, like kinetic energy, potential energy. If it was specifically kinetic energy or potential energy, they would say potential or kinetic energy on the y-axis. So the slope of this would be equal to speed of light squared. Okay? Sometimes, like I said, you'll see that sometimes on the regions. Now, one of the things we need to talk about with mass is that we can also refer to mass in universal mass units. Okay, one universal mass unit. And the energy equivalent to one universal mass unit is 9.31 times 10 to the second mega electron volts. And that's on the cover of your reference tables, and every now and then you're going to have to convert using those. They might give you the mass of a neutron or a proton in universal mass units, and you therefore have to then convert it into energy in mega electron volts. Now, there's also something called binding energy or mass defect. Okay. Now, the mass defect comes about if we take the mass of individual subatomic particles. So let's say we have, 2 protons here and 2 neutrons. On their own, they have specific masses, but together, the whole nucleus weighs less, I should say has less mass, than the individuals. If we added up the individual particles. Okay? And the idea being that some of the mass of those particles goes into the energy that binds them together. So we call that the binding energy, or the mass defect. And when we talk about matter, we also have to talk about antimatter. Antimatter is same mass as regular matter, just opposite charge. And antimatter and matter can annihilate. So annihilation is when matter and antimatter meet. We get annihilation. Okay? And essentially what that is it converts all of that matter, whether it's anti or regular matter, into energy. And that energy can then be turned into light. It can be all sorts of different types of energy. Okay? Now, in terms of what all this stuff is made up of, quarks. Okay? Quarks can either have charges of positive 2/3 or negative 1/3. And of course, antiquarks, okay, those are exactly the same, just opposite charge. So let's say, for example, an up quark, which we just call a U, has a charge of positive 2/3. An anti-up, which is just an up with a line drawn over it, is negative 2/3. Now, when we classify matter, we'll talk a little bit about classification of matter since we're on the topic of quarks here. There's 2 different types. There's leptons and there's hadrons. Okay? Leptons, we'll just draw over here. These are their own little separate category. These are electrons and neutrinos Very, very tiny. They're smaller than protons and neutrons, and they are the very basic particle in that category. Okay, remember neutrinos, so small that they rarely interact with matter themselves. And under the hadrons, we have baryons and we have mesons. Okay. Now the baryons are made up of 3 quarks. These are things like protons and neutrons. Okay, and a whole variety of other subatomic particles that we don't even talk about, but they do exist. So, for example, protons. Okay, that's an up, down combination of quarks. So that's positive 2/3 for each up and a negative 1/3 for the down, giving us a total charge of positive 1. Okay, baryons can have possible charges of positive 2, positive 1, 0, negative 1, and negative 2. Those are our only options, because any 3 combinations of quarks can't get us more than positive 2, and any 3 can't get us less than negative 2. A neutron would be an up, down, down. So up is positive 2/3, each down is a negative 1/3, which gives us a charge of 0. Okay. Protons and neutrons are always made out of ups and downs. And the other quarks, like I said, they're out there. They exist. They are combined in groups of 3 to create other subatomic particles. But the basic ones, like the protons and neutrons, those are made of first generations, just ups and downs. Now, a meson is a quark and an antiquark. Okay? It has to be one of each. And it also has to have a whole number charge. It can either be positive 1, 0, or negative 1. Those are the options there. Because any combination of a quark and antiquark is not going to be greater than positive 1. Any combination is not going to be less than negative 1. Okay? So, for example, maybe an anti-up and, let's see, what else would there be? And maybe a, let's cheat real quick here, and a charm. Okay? So an anti-up and a charm. That's negative 2/3 here and positive 2/3 here for a total of 0. It could be an anti-top and a strange. That would be negative 2/3 and negative 1/3. But it has to be a regular quark along with an antiquark. The last thing we'll talk about are the 4 basic forces in nature. Okay. The weakest is gravity. Acts over very, very large distances, but is very weak comparatively to the other forces in nature. Then we have the electromagnetic force. Okay, this is the attraction between oppositely charged objects, or the repulsion between them. Again, acts over a fairly large distance, but still not incredibly strong. And then we have the weak nuclear force. Okay, also known as the weak force. That happens only during one specific type of fission called beta decay. Not very common, typically only on stars. And the last one, strongest one, and aptly named the strong nuclear force. Acts over incredibly tiny distances like the weak nuclear force, and that's what holds protons and neutrons together in the nucleus of an atom. Okay? Incredibly strong, but only over very, very short distances. If you have any questions about any of this stuff, these are the basics, like I said. If you have any questions about any of this stuff, just stop in and see me and ask. That's the last review video. Hopefully you watched these. Hopefully you're doing some practice regents exams. Hopefully you're looking through that review sheet that I gave you. And hopefully I'll see you at the review sessions before the tests. If I don't, I wish you the best of luck. You're probably going to need it.